Okay, we are surprisingly enough still on chapter 14. We are halfway through. Now the real chapter 14 comes here. So last time we talked about acid bases, again, weak acids, weak bases, and how to calculate polyprotic acids. We're now going to get into sort of the second half of this chapter, which deals with two of the topics that oftentimes will give people a very difficult time, and that is buffers and titrations. So we're going to talk about buffers and titrations. This is where conceptually what is going on is really, really important in this part of this chapter for sure. The good news is a lot of the calculations are stuff that we have done before. The bad news is sometimes if people go on autopilot, they do the wrong calculation because that is not what's happening in the problem. So this is definitely where the conceptual aspect of what's going on, you do have to really understand sort of what's happening, where you're at, say in a titration, what's going on in a buffer to apply the correct calculation. Otherwise, like I said, you'll do a pretty long calculation for no reason because it's the wrong one to do. So just try to think about, what's going on when we do these problems, and that'll be very, very helpful. So let's get into it, which is the first thing we're going to talk about is something, maybe there it is the idea of what is known as the common ion effect. And the common ion effect is pretty much what the name sounds like. We have a common ion that's in a solution. And typically speaking, when we see this common ion effect, it involves weak acids or weak bases. So when we have a weak acid or weak base in a solution and we have a common ion present, it will typically suppress the weak acid or weak base from basically breaking apart. It essentially will keep it together. So for example, if we had acetic acid, which is a weak acid, when it's in solution, it will break apart into H plus and acetate. So again, in solution, you basically have that equilibrium being set up of the acetic acids floating around. It is mainly the main thing that's floating around. I'll put the arrows. They're floating around too, maybe in the beaker. And we also have some H pluses floating around, a little bit of those guys, and a little bit of our acetate floating around in the beaker to begin with. So if we have this acetic acid in that beaker, it will set up that equilibrium. But if we take that acetic acid and we add something else to it, like say sodium acetate. Sodium acetate is a salt. And because it's a salt, it's actually an ionic compound, which is a strong electrolyte. So unlike acetic acid, which will set up this equilibrium because it's a weak acid, it's a weak electrolyte, sodium acetate, when it goes for a swim, is essentially just going to break apart into its ions of sodium ion and acetate ion. It is a one-way street. There is no equilibrium being set up. It's all going to break apart into here. So basically, when we do that, what we're essentially adding to this beaker is those ions basically go for a swim. Now, what's going to happen in this particular case, because we have now an additional common ion in play, is it's going to have an effect on that acetic acid equilibrium. Obviously, you could probably see that the common ion that we are talking about in this case is the acetate ion. The acetate ion is in the acetic acid that has broken apart, is also coming from the sodium acetate, which is a source of acetic acid. So essentially what we're doing when we add this sodium acetate to the solution of acetic acid is we are increasing the concentration of the acetate. And since this is a equilibrium, and our friend Le Chatelier's principle would tell us that if we increase our acetate, the equilibrium should shift which way? Got a choice of like right or left. What do you think? It's going to shift to the left, right? It'd be adding more product. It's going to shift away. Yeah. So by adding the acetate here, it would be essentially like dumping in there more product to this equilibrium, which is the acetic acid equilibrium. It's going to cause it to shift to the left. And if it causes this acid to shift to the left, the acid is going to break apart more or stay together. It's going to stay together, right? Because it's going to shift it to the left. And when it does so, it will keep that weak acid together because of the presence of that common ion. And that's what it means when it talks about that a common ion present will have the effect of keeping basically a weak acid or weak base pretty much together, right? It's sort of preventing them in a sense from fulfilling what they want to do, which in this case is basically drop its H plus off for the acetic acid. If you're talking about a base, it would prevent it from producing more OH minus, but in this case, we're looking at the acid, so it prevents it from making more H plus. So by shifting this to the left, it will keep our acetic acid together. And that's going to have a pretty big effect, perhaps, on the H plus concentration. What should happen to the H plus concentration? Should it go up? Should it go down? Should it stay the same? If it shift to the left here, H plus concentration should go down. Yeah, because we're now have a lot more of this guy, which means we don't have it breaking apart as much. And the double jeopardy question is, if the H plus concentration goes down, what happens to the pH? Goes up. Goes up. Yes, so it goes up in that case, right? May not go basic, but it will go up from where the pH would be if it is what we had with just acetic acid by itself. So these presence of common ions have a pretty bad effect in a sense on an acid and base doing what it wants to do, which is basically break apart. It will basically do the opposite. It will kind of keep it together more. And the result of that is, in the case of an acid, you would have a lower H plus concentration, and that would basically make it a higher pH than it would if it was just a weak acid by itself. Again, it might not be basic or anything like that, but you would have a higher sort of acidic pH than just the weak acid by itself. The same sort of thing is true for a base. It works kind of the same idea. Instead of in a base situation, it will keep the base together. And by keeping the base together, it's going to prevent it from making OH minus. And that will keep the concentration of OH minus down a little bit, which means the concentration of H plus goes up. And that means that the pH will actually go down in the case of a weak base. Again, may not go into acidic territory, but it would be a lower pH than you would see if it was just the weak base by itself. Any questions on that there? And again, that is what we see here with sodium acetate. Again, even though both of these things are in solution, it is only going to be that acetic acid that's going to set up the equilibrium like we just talked about there. And again, we're essentially adding more acetate, causing that guy to shift to the left. And again, basically keeping our weak acid together. So let's take a look at a couple of problems here, which maybe deals with a common ion. The first one does not, so why don't you try that one? Calculate the pH of a solution that is 0.2 molar acetic acid. Let's see what you come up with here. So just do part A, Ka for acetic acid down there on the bottom, 1.8 times 10 to the minus 5. Okay, so let's take a look at the first one here. So A, we're looking for the pH of a 0.2 molar acetic acid solution. We have a Ka value given to us, Ka of 1.8 times 10 to the minus 5. We've got a 0.2 molar acetic acid solution. So we're looking for the pH of this guy, and we should know obviously from this information here, this is definitely a weak acid, and that means that we should do an ice table here. So this is just like we talked about on the first part here of chapter 14, just basically a Ka problem. This weak acid is going to dissociate into H plus and acetate here. And we will have our Ka that equals our 1.8 times 10 to the minus 5. Initially here we'll do an ice table, 0.200 change minus x plus x plus x Means when we get to equilibrium here, 0.2 minus x, and x. Any questions on that so far? So really just like a regular Ka problem that we did before, that means we should go into our Ka expression, which is our products over our reactants. And we're going to put our equilibrium line in here. So that's going to give us basically x squared over 0.2 minus x equals 1.8 times 10 to the minus 5. We're going to perhaps make an assumption because why not? And that is going to get us here x squared divided by 0.2. Remember that again, when you make the assumption, you could do that because the K value is small. And the only x's that you should get rid of, again, are the ones you're going to subtract from a number or even add to a number. We're going to multiply to the other side. We'll then do a little square rootage. And that is going to get me something like square root. Give me something like 0.001897. We do always want to check, so we'll divide that by 0.2, times it by 100% to check it. And if we divide by 0.2 times it by 100, you're like at 0.9%. So this is a good check in this case. So in terms of the pH, we are interested in the H plus concentration, which is X in this case. So this would equal our H plus concentration. So that means we could go directly into our pH. pH equals minus the log of basically 0.001897, I believe. And that will get us here. Minus the log of that there. And that looks like we're going to open up here with a 2.72 in our pH here of our weak acid. Any questions on that calculation there? So that is, again, pretty much a straightforward weak acid Ka type problem like we did previously here. So let's take a look at part B and see how it's different. So looking at part B of this problem, we have a solution that is still 0.2 molar acetic acid like it was in part A, but we also have 0.3 molar sodium acetate in it. So let's take a look at that. So this one, we have our 0.2 molar acetic acid. And in it with it 0.3 molar sodium acetate. And we still have a Ka problem here at 1.8 times 10 to the minus 5. So in this case, we do have still a weak acid. So that is the thing that's going to really set up the equilibrium here. So we'll have the same equilibrium we had previously, which is our acetic acid breaking apart into H plus our acetate. Now we also have this salt here, which is our sodium acetate. That again is a strong electrolyte, which will not set up an equilibrium. That again, when it goes for a swim, is just gonna break apart into ions here. So we'll get some sodium ions and we will get some acetate ions, right? So this is going to be a common ion type problem as the sodium acetate is going to supply some more acetate to this equilibrium. And we can figure out how much acetate by, again, understanding how molarity works, which hopefully you do. It is a 1-to-1 relationship between that and the sodium ions, which means it would be 1 times 0.3 molar and be 0.3 molar for our sodium, which is not really important in this problem, but it also is a 1-to-1 relationship between the acetate and the acetic acid, which means we would also take 1 times 0.3 molar and we would have 0.3 molar. So this sodium acetate is supplying basically 0.3 molar of acetate ions into this solution. So initially here we have 0.2 molar. We have 0 here, and this is really the important part of this common ion table, which is the part everybody leaves out. We actually do have an initial concentration of our acetate that is being supplied by the sodium acetate here. It is not 0. If you put 0, what type of problem are you doing? The exact same one we just finished in part A. We were basically just doing part A again, which is just the weak acid by itself. So it's really important that if you recognize that it is a common ion and that you're doing an ice table like this, you got to have the initial concentration on the other side. Otherwise, you're really just doing the weak acid or weak base problem, depending on which one you're doing. And obviously, it will not be correct. So that's a really big thing people mess up on these type of problems, is because it's like autopilot at this point, like 0, 0 on that side to start with. So people always kind of zero out the other side. All right. The rest of the ice table here is pretty much going to be similar to all the other ones. We're going to do a minus X. We're going to do a plus X. We're going to do a plus X here. We're going to get a 0.2 minus X and a 0.3. The second mistake that people make is they're used to minus X's, but this is actually plus X here. So make sure, again, you don't minus it, just automatically doing it that way as well. All right, so we're going to go into our Ka expression, which again is based off of our weak acid, which is really the only thing setting up the equilibrium in this solution. So putting it in there, we get X, we get 0.3 again plus X divided by 0.2 minus X is going to equal our same Ka value, 1.8 times 10 to the minus 5. We used the assumption previously, so why not give it another go here? So we're going to assume that X is equal to 0. In this case, again, it's going to be the X's we are subtracting are adding to a number that we're going to get rid of. Clearly, you can't get rid of all of them or you got nothing to solve for. So that's going to give us X times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. Going to multiply that guy and then bring this guy and divide, right? Bad dividing sign there. All right. So if we do that there, we will get 1.8 to the minus 5 times 0.2 divided by 0.3. Going to yield us here a X value of 0.000012, I believe. We're going to divide this by either number, 0.3 or 0.2, if you like. So we'll divide it by 0.3 times it by 100. And once again, we're like 0.004. So the check here, once again, is good. That will be our H plus concentration, as we can see from the table. So that's going to be our H plus concentration. And again, that is all we need here to basically put into our pH equation. And that would get us a pH of minus the log 0.0040, I think. 12. Find that on this calculator. There it is. And we're going to end up with a pH of 4.92 in this case. A question on that calculation. So again, those are two very common pitfalls, zeroing out the initial side, so subtracting the product side there instead of adding. Any questions on that there? Now, did we see here in this actual example what we expected to see based on Le Chatelier's principle? Well, with no common ion there, the H plus concentration was 0.0019, we'll call it. With the common ion there, causing the equilibrium to shift to the left, we see that the H plus concentration dropped to 0.00012. So the H plus concentration came down because the acids staying together. The result of that is, again, in terms of the pH, acid by itself 2.7. We see the pH now go up because the H plus concentration went down. with the presence of the common ion. So here in the actual problem, we could see the effect of the common ion by suppressing that weak acid from breaking apart. Any questions on that? Yeah. For are you asking between these two? Like, how do I know what's what? Yeah. So first off, this is pretty much going to be an acid because I know it has a Ka value. And because it does have a Ka value, I do know it's going to be a weak acid because of that. Um, Typically, acids don't have spectator ions like sodiums, potassiums, and stuff like that. So because that's sodium acetate, or it could be like potassium acetate, lithium acetate, whatever you want, those are basically a spectator ion as a result of the reaction between an acid and a base, basically. And that's how I know that's a salt and will be very much like a strong electrolyte and will break apart and won't set up an equilibrium. And if you think about it, it is basically our sodium and our acetate, right? So if you look at just these two guys together, the relationship between those two, that is a weak acid. And really acetate is because basically conjugate base on the other side. And that's how I know that, the acetic acid will be the weak acid because really the Ka value is also not one of those kind of 6 strong acids we talked about. But definitely in most cases, something with like somebody from group 1-ish, 2-ish occasionally, and it's going to be probably more of a salt and not going to set up an equilibrium. Definitely won't be an acid. Yeah. Have anything, it will be more of a conjugate base if it would go through hydrolysis, like we talked about, right? So that CH3COO minus will act as a base with water and go through hydrolysis that we talked about earlier on in this chapter. Other questions? And it's really able to do that because as it goes for a swim, it's able to find water in there and start reacting. Other questions? So in problems like we just saw that involve the common ion effect, for the most part, the common ion effect is really buffers. Yeah. Buffers are pretty much a common ion effect that's happening. And if you have that type of situation, either a buffer problem or maybe you recognize it as just a common ion problem, um, and the starting concentrations are relatively big or relatively a good amount, as long as basically these concentrations are relatively high, what we usually see is the starting concentration and the ending concentrations are relatively the same. So what that means, if we go back to my example here that we just did, this was the concentration basically of my weak acid. This is basically my X value, right? That I got, which means value into my equilibrium concentration, it will pretty much still be what number? It will still be basically 0.2, even though it went down a little small amount. And the same thing here, I had 0.3 to start with. And if I put my X value into here, my really conjugate base concentration will still be pretty much 0.3. So the result of this common ion effect is it definitely suppresses that dissociation. And basically what you start with in terms of, say, the weak acid and conjugate base, or even if you're doing this with a weak base and its conjugate acid, will basically be the same concentration at the end as it was basically at the beginning. And because of that, a nice thing happens, which is you might not have to do an ice table if you don't want to. You could use a relationship that allows you to calculate the pH of a situation like this, which is really a buffer situation or a common ion situation. And this is known as the Henderson Hasselbalch equation. And the Henderson Hasselbalch equation is the pH is equal to the pKa value plus the log, basically the concentration of the base over the acid. And the pKa is found, as you can see down here, by taking minus the log or negative the log of the Ka value. So you could do pretty much the problem we just did by just plugging it into this equation. And you could get it because it is a common ion problem. This equation should only be used in a buffer situation or a common ion situation, which is the same thing basically. So it has to be really a buffer situation and a common ion situation. The problem with this equation is people learn it and want to use it in every situation. And it is not to be used in every situation. It is specific for common ions, which are buffers. And we're going to talk more about buffers in just a second, but basically it's specific for that situation. If it is not that situation, you definitely should not use it. And that, again, is a very big problem people do. They just like pop it in. They're like, I got two numbers, perfect. Let's just go into this equation and calculate the pH. So you cannot just randomly use it. You have to use it in the appropriate situation. Now, there is also a couple of other relationships that we'll talk about here as well, but the pH is equal to pKa plus the log of the base over the acid. And again, the pKa is equal to minus the log of the Ka value. There is also, much like there's pH and pOH, there is a pOH version of this equation, which is the pOH is equal to the pKb plus the log of the acid over the base. So it is reverse, and it is the pKb value. The pKb value is found by taking negative log of the Kb value. So there is a nice relationship between, by the way, the pKa plus the pKb value equals 14. Kind of like the pH plus the pOH equals 14. So this can be useful in several situations. If maybe you got like a Kb value, you need a pKa value, you could calculate the pKb, subtract 14, you have the pKa value, right, really quickly. Now, sometimes people, as we'll talk about buffers, will use the equation on the left there, the pOH equation, when the buffer situation is more basic. And some people will use the one on the right if it's more acidic. The truthful answer is which one you should use. In my opinion, I would just roll with this one no matter what the situation is. It could be a basic situation, it could be neutral, it could be an acidic situation. It doesn't matter. I would roll with that one. And the reason for that is I would say probably 9 times out of 10, the question is going to ask you, what is the pH? Not what is the pOH. So if you use the one on the left, you get the pOH and you still got to subtract 14 at the end anyways to get to the pH. So you might as well just cut out the middleman and just roll right into, the pH, the Henderson Hasselbalch equation that will just get you the pH. But again, if you use this one, sometimes people will use it. You still need to, in most cases, do one more step afterwards to get what you're looking for, which obviously is subtract the 14. Any questions on that there? So to see how this works here, if we take a look at the problem we just did there, you find it there. We just did Ka was 1.8 times 10 to the minus 5. We have the acetic acid at 0.2 molar. We had our sodium acetate at our 0.3 molar. So now, as soon as you could recognize that these two things are basically related to each other, and hopefully you could recognize it, that basically acetic acid and the acetate are related to each other. This is basically, as I mentioned a second ago, a weak acid and its conjugate base. And if you could recognize that the only real difference is one H plus, you could roll right into the Henderson Hasselbalch equation. You do not have to do a nice table. You could go our pH in this case, bless you, pKa plus the log of the base over the acid. We'll calculate our pKa value minus the log of 1.8 times 10 to the minus 5, which should give you 4.74, a number you'll become very familiar with because everybody loves acetic acid as the universal example for buffers and stuff. And we can then go into our equation. The pH is equal to 4.74 plus the log. Now, again, if you are not sure which one is your acid and which one is your base, there are several things usually in a problem that can help you decide that. Perhaps you are given a Ka value, so that thing obviously would be your acid. Also, an acid does what? It donates a H plus, which means it should have one more H plus than the other guy. And that should be your acid in that situation. So if you look at acetate, it is missing one H plus. The acetic acid guy has one more H plus, which allows it to be given away, and that would be your acid. So usually as well, the base has, again, like a sodium, a potassium, some other type of spectator ion that's in there. So we want to make sure we get the right numbers here and go 0.3 on top, which is our base, over our acid in this case. And if we do that there, we want to divide first. So 0.3 divided by 0.2. We then want to take the log of that. Then we want to add it to 4.74. And that's going to give us a pH of 4.92. And dare I say that is the same pH we got here through the ice table. So you can do these problems two ways. It's up to you, whichever way you want to do it. If you could recognize it as a common ion or a buffer, you could go right into the pH equation and be done with it. You could still do the ice table if you're not sure. Again, if you choose the ice table approach, like we talked about, you want to make sure you got that initial concentration over here, which again is a very common mistake that people make. So I would say if you can confidently identify it as a common ion buffer type problem, I would go into the Henderson Hasselbalch, probably less room for error. But if you're comfortable doing the ice table and you want to do the ice table, you can. Just watch out for that very common mistake of zeroing out the right-hand side of the initial line. Any questions on that there? All right, so let's try one here. What is the pH of a solution that contains 0.3 molar formic acid, which with 0.52 molar potassium formate? Ka value there, 1.7 times 10 to the minus 4. Okay, so let's take a look at it. So we have 0.3 molar formic acid, and we have 0.52 molar potassium formate. Again, the Ka does go with our acid. You should hopefully be able to relate these guys as being related to each other. Again, the potassium isn't that important here, as this guy would break up into this and this, right? So we're really looking at the relationship between these two. And again, we could hopefully see that it is, again, a weak acid and its conjugate base. The only difference there is one H plus. If you wanted to take the ice table approach, you would take the weak acid, which is the only thing that would break apart here, into an equilibrium, or I guess set up an equilibrium. And you would have this. Your initial here would be 0.30. And once again, if you chose the ice table approach, the potassium formate is going to supply 0.52. Again, cannot be 0 in this case. Change going to be minus x plus x plus x. Gets you 0.3 minus x, x, and 0.52 plus x. Obviously, this would go into your Ka. You would solve for x and so forth to get to your pH, basically, because that will equal your H plus. Now, because you did recognize, hopefully, that this is related to each other, you could just skip all that, basically, and you could go right into your Henderson Hasselbalch equation. We could calculate our pKa value, which is negative log of the Ka, which is negative log in this case of 1.7 times 10 to the minus 4. And that's going to get us there. 3.77 looks like, maybe. That means that the pH in this case would be 3.77 plus the log. Once again, this guy with the extra hydrogen is going to be my acid. If you're not sure, that means the other guy will be my base. So the 0.52 over the 0.3 in this case. So 0.52 divided by 0.3, take a little log of it, add it to 3.77. And like a 4.01 would be our pH in this case. And again, if you go through the process there, with the ice table, you should end up basically there as well. Any questions on that there? Okay. All right, so take a look at another one here, I think. Actually, let's talk it. Let's actually talk officially about what buffers are and sort of how they work. Pretty much what we've been talking about here with our common ion effect are pretty much buffers. Those problems that we just looked at, really the one with the acetic acid, the one with the formic acid, and its counterpart, conjugate partner, are really buffers. So what is a buffer? A buffer is a solution that's made up basically of one of two combinations. It can either be a weak acid and its salt of its conjugate base, or you could have a buffer that is a weak base, and the salt of its conjugate acid. What is the difference between the weak acid and conjugate base, or the weak base and the conjugate acid, is our Bronsted-Lowry definition of just one H plus difference. The salt means, frankly, that the conjugate partner has like a sodium, a potassium, one of those guys kind of hanging out there, not really doing much. It's kind of, again, a spectator ion. So like we saw in the previous two examples, sodium acetate, the sodium is, and then the acetate together is what makes it a salt. It has a spectator ion. And the potassium formate, the K there that we saw in the last problem, is basically what makes it a salt. So they both actually has to be present in the solution to be a buffer. You cannot just have one or the other. They both actually has to be in there swimming around together for it to be a buffer. What is a buffer? People have a very wrong definition of buffers a lot of times. People oftentimes think that a buffer means that the solution is neutral, and the answer is that is not the definition of a buffer. Definition of a buffer is a solution that can resist changes to a pH, even when you add additional acid or base to it. You could have a buffer that is neutral. You could have a buffer that is acidic. You could have a buffer that is basic. You can make a buffer at any pH you like along the way. It could be a buffer. It just means that once you have your buffer solution, say at a pH of 5, when you add acid to it or you add base to it, it's able to maintain pretty much the pH at 5. It may go up a little bit, may go up down a little bit, but you will not see a giant jump in the pH if you made a proper buffer. So for example, if that pH of that buffer was 5 and you added acid to it, maybe it just goes down to like 4.9, but it will not go from like 5 all the way down to a pH of 1. There won't be a drastic drop in the pH. And the same thing if you added a base to that buffer at a pH of 5, maybe it goes up to 5.1, a little bit up, but it will not go from like a pH of 5 all the way up to like a pH of 12 or 13 if you add base to it. So if it's a properly working buffer, it's able to basically maintain its pH even when you add acid or base to it. So it basically can maintain its pH when additional acid or base is added. So let's talk about really sort of how it's able to pretty much do that. How is a buffer able to not jump pH crazily, go up really high or really low when you add acid or base to it? So let's talk about how that happens by looking at something that is not a buffer. So if we have water, which is not a buffer, and to this water, if I added some HCl, some hydrochloric acid to water. So over here, I got a little beaker. It's got some water in it. I throw my HCl in there. Careful, throw it. When HCl goes in for a swim, right? It is a strong acid, which means it is going to 100% break apart into H plus and Cl minus ions, right? So when that guy goes for a swim, I have just dumped into here a ton of H plus ions because it will not stay together. It will completely break apart and some chloride ions. Now, what I just did to this water, which is not a buffer, is I now have a tremendous amount of free H plus in that solution, which means in that water solution, the concentration of H plus went up pretty much a lot. What's going to happen to the pH? It's going to go, pH is going to go down a lot, yeah? Because you just influxed into there a bunch of H plus freely floating around. That's going to have a pretty drastic shift in your pH of that solution. So let's just say you had neutral water somehow, but you had a pH of 7 for your water. Maybe the water goes from 7 all the way down to like a pH of 2, right? A pretty big drop in the pH of it because of that big influx of H plus into that solution, hence why water is not a buffer. Question on that. So what happens if we take to water and not add a strong acid to it, but we add a base to it? So we add, say, something like sodium hydroxide to it. So same idea here. We have our little beaker here, water. We're going to take some sodium hydroxide. It's going to go for a swim. And when it does so, it is a strong base, which means it is a strong electrolyte. It also will 100% break apart into sodium ions and hydroxide ions. So 100%, just like up here, this was 100% what would break apart. That means that when we look at the solution, I just dumped in there a bunch of sodium ions floating around, which is not that important. But more important in terms of the pH is the amount of hydroxide ions that are floating around. That is a bunch of free hydroxide ions. We know the relationship of hydroxide is this. As we see in this example, the concentration of hydroxide will go up. That means the concentration of H plus will go down, and the resulting pH will then go up, right? So here again, we would see a fairly significant jump in the pH. Maybe again, it starts at 7 and jumps up to 10, 11, 12, something like that. So a really big jump in pH. Again, because water cannot handle, in a sense, all the OH minus that's coming in. It's not going to be able to do anything with it other than let it float around. And because it can't do anything with it, we're going to see that big jump in OH minus, big drop in H plus, and the pH then will jump pretty big. So this is why if you add acid or base to water, which is not a buffer, you will see this pretty big jump in pH one way or the other, because you're either inserting a lot of H plus into that solution, or you're inserting a lot of OH minus, and both of them will have the effect on pH of drastically changing it because you just put a bunch of free ions in there that's going to affect it. Any questions on that? So let's talk about what would happen if we did a buffer solution and added these same things. So just to be different, we will not use acetic acid and sodium acetate like every other one. We'll go with hydrofluoric acid, why not? And sodium acetate. It's also less letters to write as well, by the way, as our buffer. Again, I can recognize this as a buffer solution, hopefully, because HF is a weak acid. And again, this sodium fluoride is really a sodium ion and a fluoride ion. So it is really right there. The buffer part of it is conjugate base. Again, the difference between HF and F minus is just one H plus. The sodium here is not of any concern because sodium is just a spectator ion. We also know that sodium is what type of salt? It is a neutral salt, like we talked about with hydrolysis, right? So even if it's floating around, it's not going to affect the pH in that solution. Just why as well for the sodium hydroxide, it didn't matter all the sodium ions floating around. It's not going to have an effect on anything. It won't affect the pH as it's neutral. So when we look at this, this is our buffer, basically, these two guys. is really the buffer part of it. It is the acid part of the buffer, and this is the base part of the buffer. And remember that we need both of those things in the solution to begin with. And when we do that, if we look at our buffer beaker here, that's a mouthful. Out of these two things, the HF and the F minus, the only one that's going to set up an equilibrium in the solution is the weak acid, which is HF. And that's okay because it's going to set up this equilibrium, and those arrows floating around as well. It will set up basically this. Okay. Now you may be saying, okay, so why do I need this? Well, when you add sodium fluoride, what you are doing is basically adding some more fluoride here. That's going to keep the concentration of the fluoride in that solution relatively high enough to work as a good buffer. It will also keep the concentration of HF relatively high. So by adding F minus here from the sodium fluoride, you're kind of just beefing up the F minus concentration that's in there. Because remember, HF is a weak acid, which means it's not going to break apart a lot, right? And make a lot of F minus. So you're kind of helping it out to make it a buffer by adding a little bit more F minus to that solution. So now you'll have a relatively good amount of HF, which is the acid part of the buffer floating around that solution. By adding some more sodium fluoride, you're going to kind of beef up the F minus ions that are in that solution. So now what you have is a solution that has a relatively good amount of acid part, the HF in this example, and base part of the buffer, which is the F minus in this case. So basically, this is our buffer beaker, and it has the two main components that's necessary for it to work properly. Before we even did anything, before we added anything else, we have the acid part of the buffer, and we have the base part of the buffer. We also have an initial amount of H plus in there, and that's really what we're going to try to keep constant and not change all that much. Any questions on sort of the setup? So this is what your beaker is looking like before you even dump anything in it. We got to have both of those things in there at relatively good concentrations. If we just did the hydrofluoric acid by itself, it probably would not produce enough F minus to work effectively as a buffer. So that again is why we need to add that extra sodium fluoride to kind of beef it up so that it has a good amount of concentration to work as a buffer. So now that we have our buffer, what's going to happen when I add my acid to it? So we'll take the same acid that we just used previously, and I'm going to add my hydrochloric acid to this guy, right? So I'm going to take my HCl, and it's going to drop in. And we know that HCl is basically going to come in as H plus and Cl minus, right? So that's basically what's going to drop in. When I add hydrochloric acid to this buffer, it's going to react with the acid part of the buffer or the base part of the buffer. It is going to be the base part of the buffer, right? They're called acid-base reactions, right? Not acid-acid reaction. So they are acid-base reactions. So when you drop this acid in there, you're going to get a reaction between the hydrochloric acid and the base part of the buffer, which is the sodium fluoride. Again, really the fluoride part is the important part here. The result of that is you're frankly going to get a double exchange here, right? Double displacement. They're going to switch partners. And you will make HF, and you will make some sodium chloride in this case. Any questions on that there? So let's look at what we just made here, right? So we actually made more of the HF, which is part of the buffer to begin with. So clearly that is not going to mess up the pH because we just made more of what was there to begin with. So that's not going to have any effect on pH. So really when we drop this in here, the H plus ion, the Cl minus is not important here. It's a spectator ion. It's a neutral guy floating around like a sodium would be. It is going to go find the F minus, and it's going to make more of the HF, right? And that will not affect the pH. We will make this salt here, right? What type of salt is this? It is a neutral salt, which is why we don't really care about the sodium ions and the chloride ions floating around. It's not going to do anything with the pH. So we actually did not make anything that would mess up the pH, but it is actually what we do not see in this equation as to why the pH will remain relatively constant. What do we not see on the product side of this equation that we did see on the product side of when we added acid to water? What is not there? There's no H plus. There is no free H plus here. There is no free H plus because, as I just said a second ago, my free H plus that came in combined with my fluoride to make this guy. So it is not freely floating in the solution. So what that means is we did not make any more free H plus, which means the concentration of H plus will stay relatively constant. And that is what we were talking about at the beginning here, which is the amount of H plus we started with in that beaker will pretty much stay the same because there's no influx of H plus like we saw happen when we added it to water, right? When we added it to water, there was a ton of H pluses everywhere. But in this case, that H plus gets pretty much tied up with the F minus and makes HF, which means it's not free to just freely roam around and affect the pH. It gets pretty much tied up. And because the H plus stays relatively constant, that means that the pH in this situation will stay relatively constant as well. I say relatively constant because the truth is if you add acid to a buffer, you will see the pH go down a little bit because you are now increasing the amount of HF, which will break apart a little bit more, and will add just a little bit more H plus than was there to begin with. But you will not see a ginormous jump in pH. So again, this would be a situation where maybe the pH just drops a little bit. Maybe it goes to like 5 down to like, 4.9 or something like that. But it will not go, again, a giant jump, say from 5 all the way down to 2 or to 1, because you don't have that enormous amount of H plus coming in. Most of it is going to get tied up with the F minus. You will make a little bit more HF, but it will break apart a little bit. So it will just go down just a little bit. You shouldn't see a really big jump in pH. Any questions on that there? So what happens in this situation if we add our base to this guy? We'll go here with that one. So once again, we'll use the same buffer here, our HF, which is our acid part of our buffer. We will have our NAF, which is our base part of our buffer. And again, these guys are going to be a buffer. So again, if we draw our beaker here, we will have our weak acid again setting up that equilibrium. And again, that is going to be our buffer solution to begin with, where we still have our acid part. We still have our base part. And obviously, this is our buffer. Now, in this case, we're going to add our sodium hydroxide to it, which is our strong base. So we're going to dump our sodium hydroxide in. That, again, is going to be a source of sodium ions and hydroxide ions going in for a swim. So what's going to happen in this case is we're going to take our sodium hydroxide. it is going to react with the acid part of our buffer, right? Since it's a base, so we will get an HF reaction. Also double displacement situation happening. Switch partners. That's going to be some water. And that will be some NaF made here in this particular case. So what's going to happen in this situation is we will make some water, which obviously will not affect the pH. We will also make some more sodium fluoride, which is there to begin with and part of the buffer. So in this case, my OH minus is going to go for a swim and find some of my H plus and make some water. And again, we're also going to put some more F minus into the solution, which will cause the equilibrium to go to the left a little bit as well. And this situation here will not affect the pH because of, again, what we do not see in this case, which is what we saw when we added it to water, the base, a lot of free OH minus. In this particular case, our OH minus is no longer free. It gets tied up here in the water. So we do not have that big influx of OH minus. So no free OH minus formed. The result of that is the concentration of OH minus stays relatively constant. That means that in relationship to that, the H plus concentration will also has to stay relatively constant. And the result of that is, again, our pH will stay relatively constant as well. So how a buffer works when you add a base to it is it prevents the formation basically of free OH minus in that solution. And by doing so, it allows basically your H plus concentration to still remain relatively constant. And that will keep your pH relatively constant. Same idea here. If you added the sodium hydroxide to this buffer and you were monitoring it with a pH meter, you would see the pH go up a little bit. But again, we will not see a giant jump in pH. Should just go up a little bit if the buffer is working correctly. Question on that there. So essentially how a buffer works is you have a buffer and in that buffer, you have an acid part, which is sometimes just abbreviated as HA. You have a base part, which is A minus. And in this case, when you add more acid to a buffer, the acid will react with the base part. But as we saw, you will make more of the acid part, dramatic drawing. So we'll make more of the acid part of the buffer when you react it with something like HCl. You will use up some of the base part of the buffer. And same thing happens if you add base to your buffer. The base will react with the acid part, and we will see actually an increase in the base part of the buffer. And we'll see a decrease in the acid part of the buffer. So even though you add acid or base to a buffer, you're actually just going to use part of the buffer, but you're actually going to regenerate the other part of the buffer. So you keep kind of regenerating them. It's also why a buffer can work for a good period of time, because even though you're using part of it, you're kind of regenerating the other part, and you can kind of go back and forth and adjust the pH accordingly. Again, there's a good amount in there to start with, so you don't get these big jumps. What would happen, for example, if I didn't read the instructions, which would never happen in real life, right? Or you grab like the 18 molar hydrochloric acid instead of like the 0.1 molar, because they look alike, I suppose, the numbers. Yeah. So you grab that off the shelf and you add it. So what would happen in the case of the buffer if I just kept adding acid? I just kept going. Every time I add acid, it's going to react with which part of the buffer? The base part. So every time I add acid, I'm just going to chew this up, right? I'm going to keep chewing it up. Even though this guy is going to get bigger, I will eventually keep chewing it up until perhaps there is no more base part of the buffer left. And if I continue to add acid at that point, what am I essentially putting into that solution? A bunch of H plus at that point, right? And it's at that point that you would actually see the pH start to jump pretty high because you basically just broke through your buffer, right? And you basically have two acids in there. You have the acid part of your buffer and the H plus coming in from the acid you're adding. You got a lot of acid now in that solution. You're going to have a pretty big jump in the pH because of that. Same thing would happen in this case. If you kept adding base, you would eat up all this, right? And you would burn through your buffer. There is what is referred to as buffer capacity. Buffers only work really well over a specifically designed area. You have to make a buffer that has the correct concentration to react with whatever acid and base you're putting in there. So if you made, like I said, like a 0.01 molar buffer, and you grab like the 18 molar HCl, you're going to blow right through that buffer because the acid part of that buffer and the base part of that buffer is not strong enough to handle what you're bringing in. So it's really important when you make a buffer that you make the right concentration of buffer to handle whatever acid or base that you want to bring into it so that you don't get those really big fluctuations in the pH. You can, like I said, blow right through a buffer if you add the wrong thing. Question on that there. Now, there's also the question of how do I know how to make a buffer? Like if I tell you next week, go make a buffer, which depending on next week, I might actually tell you to go make a buffer next week. So if I tell you next week to go make a buffer, how do you know how to make it? Well, buffers pretty much use our Henderson Hasselbalch equation, right? So you could actually use the Henderson Hasselbalch equation to help you figure out what might be a good buffer to be, or what to choose to make a buffer out of. You could actually use it very specifically, like we'll do in lab, to pick a very appropriate buffer and make it a very appropriate buffer. But typically speaking, a lot of times we want a pretty good concentration of the acid and base part of the buffer. So if we started with equal concentrations of the acid and base part of the buffer, so this guy and this guy were the same number, that would essentially give me the log of 1, right? Log of 1 is 0, right? So if you have the same concentration of your base and acid that you put in there to make your buffer, that would basically zero out that. That means that the pH would equal the pKa value. So typically speaking, you would want to choose a weak acid or weak base that has a pKa value plus or minus 1 of your desired pH. So ideally, you want to find a weak acid or weak base that is really close to the pH of the buffer you want to make. But ideally, plus or minus 1 will work. Some are better than others. The further away you are, for example, in the pKa value from your desired pH, could you get the buffer made? Probably would be really effective, probably not as effective as choosing something that's much closer. So for example, acetic acid has a pKa value of about 4.74. Would be a great choice if I wanted to make a buffer at like a pH of 4.8, 5, maybe even, 4.6 something, that would be a really good one to choose. If I wanted to make a buffer at like 9.1, this would be a really crappy one to choose. You're way too far away from it. You would want to choose perhaps something like ammonia or ammonium, which comes from ammonia, that has a pKa value of like 9.25. That would be a much better choice. And you would choose ammonia and its conjugate acid, ammonium, and put them together. Take ammonia and a little ammonium chloride, mix them together in the right proportions, and you will have your buffer. So when choosing what to make your buffer out of, you want to find, again, either a weak acid or a weak base that has that pKa value that is plus or minus 1, basically, of your desired pH of your buffer. Any questions on that there? Questions on how buffers work to maintain pH? Yeah. All right, we'll wrap that up there for today.